Okay, I'm going to start by looking at problem 14-74. Uh, we have assembly consists of two blocks, A and B, which have the masses as defined, 20 kilograms for A and 30 kilograms for B. Okay, so we need to determine the speed of each block uh, when B descends 1.5 meters. Okay, so initially you have they're released from rest. Okay, and we'll neglect the mass of any pulleys and cords. Okay, so just looking at it and thinking about it first about how we might approach it. Of course, this is a work and energy problem, or what I should say is a conservation of energy problem. That's how we can deal with it. So essentially, what we're saying is like whatever initial energy these blocks have is going to be equal to whatever final energy that they have. Okay. Now, that energy is going to be made up of essentially two different components, or potentially two components, and that's going to be the potential energy due to their location relative, their relative positions along the vertical axis, um, and also their kinetic energy, right? So initially, one of the things we can say is that in their first state, just looking at it, we can recognize that, oh, they're both released from rest. So neither one of them has any kinetic energy associated with it. Okay. And then the second part of this, we have to think about if they have potential energy associated with it, that we need to have a reference point or reference line here, reference axis, if you want to think about it that way, or along the horizon. And one of the ways we can do that is just make it their position right now is zero, right? So if you think about it, it's like one is going to lose. So like when this is released, uh, B is going to go down a bit. It's going to go down to 1.5. So at that point, it's actually going to, if we want to consider that to be negative potential energy, and A will be gaining potential energy. Okay. So what we can say is that if we start this off from zero, essentially what we have is that the situation is zero potential energy and zero kinetic energy associated with the blocks at that point in time. Okay. And then in the final position, when it's at 1.5 meters, this has kinetic energy associated with it, and so does this. And the thing to recognize here is that one is going to be positive and one's going to be negative, right? Now, there are other ways to look at it, of course. One of the things you could say is you could go down by like 1.5 meters and then say, like, that's the reference point. And initially, both of them have some, potential energy associated with them, okay, from that reference point. That's another way. But if you set this at zero, it does simplify the calculations a little. All right, so that's the basic idea of how we're, thinking about how we define the problem and how we're thinking about its solution. Oh, and there's one more piece of this is that there's a relationship between them, how much these move, right? It's like, well, this one has three cables connected to it. This is all the same length of cable or rope. So if this one goes down 1.5, this is only going to go up essentially one third of that. Okay, so we have to also include that idea, right, when we go through and define this problem. Okay. Okay, so just looking at it, different ways to look at it, but what are we looking for? We're looking for essentially that velocity VB at when it's at 1.5 meters down from where it was. Okay, so it matters how we're going to define this. The way I took a look at it was similar to what the author did, was actually defining our datum point, our initial points being both being at that position. Okay. So this will be down by 1.5 meters. So these are some things that are given, right? Well, we have initial mass of each, and we know right off the bat that the initial velocities of each are 0, too, because it's at rest, right? So we're going to use the conservation of energy equation, and of course we have the two parts, whatever initial kinetic energy the system had, plus its initial potential energy, it's got to equal whatever its kinetic energy plus its potential energy in any other point, right? It doesn't really matter. in the system. It's got to be the same. Well, for us, what do we have? This basically represents the rest position when we first start, and this represents when B has gone down by 1.5 meters. Okay? So we can diagram this, and there's a relationship. We have this length L. We can define this thing L, and L is just basically 3 times whatever the length is from here to this wheel, and then plus whatever length from here to B from the center of that wheel. Okay? So that length is going to be constant, right? The portion of that of the cable that we're looking at, it's going to be constant. And if we think about it just in terms of like how these change, right? The way they change, SB changes and SA changes, is SA essentially is getting smaller, or if you want to think about it, you put the negative sign to either side, it really doesn't matter. But 3 times this length, right? 1, 2, 3 is essentially going to be equal to this. Whatever change this goes through, it's 3 times the length. This will go 1/3 distance, right? So this will change by 1/3 of a distance. So if I take a look at it and just define it, says that, and it's the negative, right? So this is decreasing by essentially 1/3 of how much this is, right? Whatever this is increasing by. Okay, so one of the ways you can write it is just say, okay, 3 times this little line is equal to 1 of these, right? Okay, so in terms of their delta, the change in them, okay? So if we take this one step further, what we can say is that the velocities, right? If you do like, the delta S over delta T, what you would find is this one is essentially moving at 3 times the velocity of this, whatever this block is moving, right? And since they're going in the other direction, it's just the opposite. One's going one way, one's going the other. We'll say that it's negative, okay? If we were just looking at magnitude, it'd just be 3 times it, but it also has direction associated with it, okay? So one is the negative of the other. So what we can say is VB is equal to minus 3 times VA. So we're saying that going down essentially is positive for VB, all right? Okay. Okay, so if I apply the law of conservation of energy, here's like our initial positions, right? And if we use their initial positions as being the datum point, what we would find is the initial kinetic energy, of course, because it's no velocity, they're starting from rest, and the initial potential energy is going to equal 0, okay? So the next step I did is broke it down into the 2 parts. Here's like my, A block, and here's the B block, the initial positions. At rest, this is where we're starting from, and this is at position 2, which is block B being down 1.5 meters, okay? So these are all 0. Right, to start with, at least if the datum point is that those blocks at rest, then you can define them all as 0. Okay, so that's going to be equal to whatever initial kinetic energy and potential energy of both of them, right? But what we recognize is that block B is going to lose potential energy. All right, so it's negative. All right, so it's going to be less than 0. All right. So everything over here is on the left-hand side, so we can set everything equal to 0. And what do we have? Then here is our initial kinetic energy. Here it is, well, for VB, right? This is my initial potential energy. Oh, no, sorry. This is the initial kinetic energy of both. So here's for VA. So this one you solve for VA. You could solve for VA and then, of course, plug it back in with that relationship of VB. Okay. Okay. So here is block A, my final kinetic energy. Block B, final kinetic energy, where in this case we just substitute in for VB with negative 3 VA. Okay. And then here is block A, its final potential energy. And notice it's only gone up 1.5 meters over 3. Okay, so this is the final potential energy for block A, and here's the final potential energy for block B. Okay, so now what you can do is just, this is actually like 1.54. You could put a 4 here, and that will come out to be the same as this one, essentially, right? And so in terms of like the final magnitudes and VA, these are actually just, negative of each other, but if you just put them in terms of magnitudes. So if you solve this, what you come up with is 1.5 for that, right? 1.5 could be, about plus or minus. We see a squared term in here. It's a squared term for VA. But if we just considering its magnitude, it's 1.5. You could actually put a 5.4 here. I just truncated it. So 1.54 is the magnitude. And of course, this is 3 times that. Back at our original equation, the relationship between the two, right? 3 times VA essentially is equal to our VB. So, this is negative 1.5 meters per second because it's going up. And then the other one, of course, is just 3 times that, which is going to be our VB, which is going down in the direction of what we consider to be positive going down. Okay? And that's basically it. That's how you would do it. Or one of the approaches, right? Because it's really dependent upon where you pick your datum point, how you're going to set up this equation. But numerically, it's going to come out to be the same, regardless of where that datum point is or your zero reference point is.